Okay, where are we? All right, color temperature. So we talked about color theory before, and what a terrible way to start a new recording, referring to when you're not watching. So let me just do a clean start. Color temperature. Okay, what are we going to talk about here? We're going to talk about what is white, who is Kelvin, and how hot is light. These are the high points of this lecture. Color temperature is a measurement. The actual definition of color temperature is a measurement in degrees Kelvin. We'll talk about that in a second. That indicates the hue of a specific light source. Okay, so understand right off the bat that color temperature is a hue measurement. It is not a chroma measurement. It is not a luminance measurement. Yes, things get brighter as color temperatures change, but that's only because the hue is shifting. They're not any brighter than things with different color temperatures. I'll explain that in a minute. It's again, it's confusing because we're conditioned to think that white, for example, would be brighter than yellow, but you can have a very bright yellow, right? So why do we call it Kelvin, and why do we measure it as temperature? Well, because this physicist, William Kelvin, this happy chappy here in the photograph, heated a block of carbon and noticed that it changed colors as it got hotter. So that became the entire basis for our color temperature system that we use today. In fact, reference black bodies, which is the technical term for that piece of carbon, are now what replace that carbon. So carbon blocks were used to calibrate color temperature for ages and ages. And then as technology improved, we now have artificial ways to have what's called a reference black body. I show up, for example, here, a piece of Vanta black fabric. And this fabric is the least reflective fabric that has ever been invented and can be used as a way to calibrate color temperature nowadays. Okay. A black body, by the way, is any material that absorbs all visible radiation. Nothing is reflected back. All is absolute. Yes, in physics, nothing is absolute. However, they consider that the theoretical black body would absorb everything. A black hole, for example, is called a black hole partly because it is a black body. All right. Sometimes black body, by the way, is one word, just so you know. I put it in two, but it's interchangeable. So why carbon? Because carbon, for one thing, is an element that is visually black at room temperature. So again, this is the basis for this scale. And so some of the stuff I talked about with the black body goes back to the fact that the first thing we used was black, which was carbon. And Kelvin felt that was essential for whatever reasons we don't need to get into. But we chose carbon because it's visually black at room temperature, which is essentially absorbing all energy, essentially. It can be heated to a very high temperature without disintegrating, right? And therefore you can have it go through all these color changes that it goes through as you heat it up. And we'll show them in a minute. Right now we use other methods, like I said, we use electronic devices. This piece of equipment is called a black body target, and it essentially replaces that piece of carbon. So that disc in the center that you see that's black can change colors to represent, and it's calibrated, of course, to represent different temperatures. So yeah, fake carbon. Why color temperature? Because it's the color of a reference at a certain temperature. It's really that simple. It's heating up the carbon to a certain temperature makes the color change. So Kelvin dubbed it color temperature. Okay, we apply this measurement to light sources, mostly. So here's an example. When Kelvin heated a piece of carbon, the first thing that happened to it was that it turned red, right? Red hot, we've seen that. We all recognize that. Well, then he heated it some more and it started to turn yellow. And you've probably seen that too. When something gets really hot, it goes from red to yellow. And then you heat it again, it starts to get even more bright, more intense, I shouldn't say bright, more intense, and that yellow turns to almost a whitish yellow, right? And finally, it turns blue-white. And at this point, we use the term incandescent. This is where the term for incandescent lights comes from, because we heat up the filament inside an incandescent light so high with so much electricity that it glows bright white. It incandesces is the term. But at the same time, this is also the maximum color temperature of theoretical objects, right? Is this bluish white. So back to Kelvin and his scale. So the Kelvin scale is a variation on centigrade. And what that means really is that the space between degrees on the Kelvin scale is the same as the space between degrees on centigrade. I say that because, or Celsius, because, and I use centigrade, by the way, because it was centigrade when Kelvin was using it. It was changed to Celsius later on. or standardized on Celsius later on. I say that because the Fahrenheit scale has different spacing between the degrees, right? Which is why the Fahrenheit scale, for example, when you talk about -40 Celsius and -40 Fahrenheit, they're the same, but 0 Celsius and 0 Fahrenheit are different because the spacing between degrees is different. But in Kelvin, the space between the degrees in Celsius and Kelvin are the same. The difference is that Kelvin starts at what's called absolute zero, which is the theoretical point where nothing in the universe would move. It's so cold that nothing moves. And that temperature is -273 degrees Celsius. Okay. Now, I don't know if we've ever actually reached absolute zero. I think they're close. They're probably at like 272 and a half, -272 and a half degrees. But because again, in physics, to get perfect absolute motionlessness is probably impossible. But that is the theory. Okay. So let's get back to the temperatures. So if we look at, this is a color chart indicating how color temperatures work. And if you imagine that we're starting at the left with a candle, and a candle kind of glows not too hot, right? You can put your hand over a candle flame and, it'd be warm and it wouldn't burn unless you're too close. Then you get to a tungsten bulb, the old school screw-in light bulbs in granddad's house or even your own home, depending. And then you get tungsten lamps, and those are different only because those are professional. So a tungsten bulb is like your screw-in light bulb. Your tungsten lamp is probably your movie light, your video lights that you can get still, and we still have them in ops. Then you move up the scale as things get brighter. I shouldn't say brighter, they get hotter. You get direct sunlight, right? 5,000 degrees to 6,000 degrees is roughly sunlight daylight. And then you get into the cooler tones, and we'll explain this confusion in a minute. You get into daylight, outside shade, and cloudy sky. So as the light source gets hotter, physically hotter, the numbers go up. The color temperature shifts to become from red to blue. So remember, on the light spectrum, right? The visual spectrum is infrared, right, which is heat, to ultraviolet. So as the energy increases, it shifts from red to blue. That is how the color temperature scale works. All right. So here's where this is again a confusing thing. The higher the color temperature value, the cooler the light is. And the lower the value, the warmer the light is, right? So I'm gonna go back to this because it's a bit bigger. So this is what causes a lot of confusion with people. You think that, well, the temperature is going up, it's getting hotter. Well, the object is getting hotter. So a candle isn't as hot as the sun, right? But the sun radiates cooler light than a candle. And that's because of human brains, because we are kind of dumb. And therefore, as the light gets hotter and brighter, it starts to shift from red to blue. Well, the thing with the hotter it gets, like the sun sort of glows yellow-white because it's not super efficient, but there are stars out there that get even hotter than the sun, and they, right, blue dwarfs, there's red dwarfs, I'm sorry, they're not hotter actually. There's blue dwarfs, there's all kinds of astronomical things like stars that glow hotter than the sun, and they turn blue, right? The sky turns blue as it gets more intense. Well, the problem with humans is, to us, blue equals cold, right? Simple. Ice cold, blue hands. I was so cold I turned blue. I mean, how many times have you heard expressions like that? Well, that's human behavior. So because of that human behavior, we sense things that are bluer as being icier and colder. That's just the way we are. So rather than fight it, whoever developed all these scales long ago, and it doesn't really matter who it was, decided that things that are bluish will be considered cool, and things that are warmish will be considered reddish and yellowish. Okay? So here we have today the color temperature scale. When somebody wants to warm up a person, they have to lower the color temperature closer to candlelight, which is only 1,000 degrees Kelvin, or 1,850 degrees on this diagram. Lower degrees Kelvin than daylight, which is at 5,500 Kelvin. Okay? I'm going to pause there for a second, because that does take a bit of processing. So the higher the color temperature, the cooler it is. Quiz question on this in the quiz. Oh, did I say that out loud? Sorry. The higher the color temperature number, the cooler the light source. The lower the color temperature number, and in fact, in reality, the lower the temperature of the light source itself, the lower the temperature of the light source, the warmer it looks. All right. So that's, I've just said all that. So warmer, lower, there's a couple of slides to this because warmer, lower, higher, cooler. Somebody wants to warm up something. When a lighting person says to you, the talent looks a bit cold, I need to warm them up. You want to lower the color temperature. You want to add some orange and yellow or red to the light. Take away some blue. And again, this is also true with color correction. This will come an issue with color correction. You often see in horror films, they use lots of blues and greens, right? Because they want to imply that it's chilly, it's cold, it's spooky, it's scary, right? Warm is always comforting. Fire is comforting. You know, warm-bloodedness. These are all psychological states. And so we use that in color temperature, color correction, and lighting, all those things together, right? Okay, here's a practical example of this. So here's three, again, these are all simulated because of course, impossible to show on a slide, but here's the simulation of the three different lights. So daylight, now what I've done here is we flipped it around to show that going from cooler to warmer by lowering the color temperature, but the daylight on the left looks kind of bluish, right? It looks cold. It looks like you can imagine that picture on the left of the office in daylight looks like a refrigerator because it's blue, because that's how we're conditioned to think. The things that are that color are chilly, right? The middle is cool, is warmer. It's called cool white because it's not as yellow as warm white. But that's how it affects. So you can see this would affect the mood. You know, if you wanted to do kind of a scary thing, you might do it on the left. If you want something kind of warm and fuzzy, you do it on the right. Daylight, cooler, brighter, higher temperature. You'll notice on the scale at the top of the screen, 9,000 degrees is cooler than 3,000 degrees. Okay, here's some more examples marked off in degrees Kelvin. 2,700, which is roughly the tungsten screw-in light bulb temperature, versus 5,000, which is getting close to daylight. And again, you can see it goes from warmer to cooler, but the numbers are going up. Okay. Anyway, and then here's some more examples. And I'll leave all these up. You know, you guys obviously will have access to this on the Learning Hub. So kind of memorize some of these numbers a little bit, especially these references. So warm white, daylight white, cool white. You'll notice now we're not into the marketing terms of crystal white and that kind of stuff. These are a bit more industry-specific type terms. Here now we're back. Now we're back to that. Just as I mentioned it, we're back to that slide. So remember that our brain will normalize white. You won't see these changes if you're only looking at one of these light sources. So if we go back to this slide and we look at the 3,000 degree light source, which is a regular light bulb, it's entirely possible you would be in that room the whole day and not notice that it looks yellow. The camera will notice it right away because the relationship the camera has to white is different than your brain. The camera is a fixed relationship in RGB. You've got to set the white balance and tell the camera, no, regardless of what your programming says, this is now white. And once you do that, everything looks normal. Everything looks white in there, and you'll be happy with it, right? But to your eyes, remember, to your eyes are color correcting all the time, which is what I just said. So then the final little bit of this presentation is common light sources and their pro light sources and their color temperatures. These are approximate numbers, okay? So a tungsten fixture, anything with a filament in it, is called the tungsten fixture. There's a wire inside that heats up, that incandesces when it gets heated up. A tungsten fixture is roughly 3,200 K, okay? So if someone wants tungsten or halogen lighting, halogen is a little bit brighter than this, you'll get a 3,200 K warmish light. They're telling you they want something warm. If you want something to look old school, like old school movies when they only had these kinds of lights, the old school color movies, they only had these kinds of lights. So therefore everything looked a bit warm, right? And here's an example of just showing you how the tungsten works and halogen works. Don't worry about this. Moving on. The next one's an HMI. An HMI, hydrarium mercury. I can't remember what the I stands for. Doesn't matter. These are called daylight lights because they run at about 5,600 K. The light they produce is roughly equivalent to sunlight in certain situations. We'll talk about that in a moment. Okay, so the HMI is about 5,600 K. So if somebody says they want something daylight balanced, a daylight fixture, for light, an LED fixture that does daylight. So if you're buying a light fixture, you want to have at least this range of 3,200 K if it's an LED fixture, and you can adjust it. It should go from at least 3,000 K to at least 6,000 K, right? So you have that range. You can use your LED for both. You couldn't in the old days with bulbs, they were fixed at 1, and LEDs now you can adjust. Fluorescent lights, not as popular as they used to be because of all the mercury and such, but they, again, if you want that old school office look, if you're doing a Mad Men type show or something that takes place in the 60s, 70s, and 80s in an office, or in a convenience store like 7-Eleven, where they I think still use these, they're about 2700K to 6500K. They look a bit greenish yellow compared to, they're seldom on the low side. They're mostly on the high side of the numbers. LED panels, like I said, you want to, ideal is to get a range between 3,000 and 6,000 if it's adjustable, if it's white and adjustable, because you want to be able to simulate any different kind of lighting that you might need. Okay. And then there's, of course, the variable ones. The trick with the variable LEDs, and I don't know if anyone's gone over this with you, is that they have 1/3 of the because they can be fully adjusted RG and B, they often have 3 LEDs, one red, one green, one blue. The problem with that is as you change the colors, you turn off some of the LEDs, so you lose brightness. So even though you can make the color balances happen, you need more lights, because as you adjust the colors, some LEDs are being turned off and some are being left on. Okay? That's just a thing to know about variable color LEDs. And you'll see that in all the reviews. If you read reviews of variable color LEDs, you'll see that they can often suffer from intensity issues, especially if you have to make radical adjustments in color. All right, and then a quick chat about colorimetry. And that is basically the science and perception. And what I want to just chat about here briefly, we talk about light sources and white balancing. It's just how the sources produce light. So colorimetry is a big, again, it's a big topic, and I don't want to belabor it. There's only a couple of slides here. We're just going to wrap up. But the CIE diagram, the color temperature, spectrum analysis of light fixtures, et cetera, these are all the things that are covered by the science of colorimetry. All right. What you really need to worry about more than anything is just how the lights produce the spectrum. And so here's an example of 4 different light sources. The far right light source is a tungsten filament light fixture, studio tungsten, so it's a professional fixture. And the other 3 are LEDs, various types of LEDs. So the one on the far left is a phosphor white, which is one of the earliest white LEDs, produces only one kind of light. It does it by mixing. You can see the peaks. It mixes a bit of blue with a bit of yellow and does a bit of tricks. Your brain doesn't see all that variation. It just sees the product. But why I'm showing this to you is because using some of these lights will change objects that they shine upon, right? So just because a light looks white doesn't mean that it's broadcasting the whole spectrum. So a tungsten light, one of the reasons a tungsten light looks so orange is that it does have a lot of energy in that orange spectrum. So it does warm it up. But you'll notice it's a pretty smooth graph. It's producing lights all across the spectrum because it simulates a natural source. The sun is an incandescent atomic furnace. So it runs on the same principle as a light bulb, the old-fashioned light bulb, by producing light all across the spectrum, which is how we have rainbows. If the sun was an LED, you wouldn't have rainbows. You'd have just a couple of colors because they only produce a couple of colors, essentially good enough. But this can change the reflectance of paints and pigments and fabrics, because they're not picking up all the spectrum, just a few. So I just point this out because sometimes choosing your light fixture, if you're really into it, can have an effect on how things look. So here's an example of the sun. So the sun, if you'll notice that the ramp on the sun, let's go back to the tungsten light. The ramp on the tungsten light is heavily weighted towards orange, hence its lower color temperature. It's warmer color temperature. The sun, on the other hand, is ramped the opposite way, right? It's heavily weighted towards blue. So it's got a cooler light, more energy in the blue than in the red. But again, all the light across the spectrum is being reproduced out of the sunlight, a full rainbow of light. An RGB, that adjustable RGB that I showed you earlier, would have this coming out of it. It would make light by mixing these 3 colors together, but there are gaps where there are no energies being radiated. Just a minor point, but enough to understand that choosing a light fixture can often change how things will look. That's all I got. I will stop the record and open it up. Oh, for questions. Stop.